Welcome to the Theory of Machines Module 4 video contents. So in the Module 4 video contents, we'll be discussing about balancing of rotating masses, balancing of reciprocating masses, and the governors which is added in the automobile application, the classification of governors, how governors are going to work, how to calculate the power of the governors which is installed in the automobiles. So in the balancing of rotating masses, we'll be discussing about static and dynamic balancing. In the static balancing, we will be able to see how we are going to do static balancing. So further in the dynamic balancing, we will be taking different rotating masses which rotate in the same plane, how it has to be balanced, and if it is in different plane, how balancing happens we are supposed to see. So further we will be able to discuss about balancing of several masses in the same plane and also in different plane. So we will be having discussion on the applications. So in the reciprocating masses, we will see effect of the inertia of the crank and the connecting rod, single cylinder engine, and balancing in multi-cylinder inline engine. So further we'll be discussing about types of governors, force analysis of Porter and Hartnell governor, controlling for stability, sensitiveness, isochronism, effort and power, and their applications on different governors. So further we'll see what is balancing. Balancing is produced in rotary and reciprocating machinery due to inertia forces associated with the moving masses. So here when we do balancing, when it is rotates in the same plane or multiple plane, we are supposed to see that there is a perfect balance. There won't be any motion from the initial position. So here the process of designing or modifying machinery so that unbalance is reduced to an acceptable level and if possible is eliminated entirely. So here when a particle moving in a circular path experiences a centripetal acceleration and a force is required to produce it. An equal and opposite force acting radially outwards act on the axis of rotation is known as the centrifugal force. The disturbing force on the rotation on the axis of rotation, the magnitude of which is constant, but the direction changes with the rotation of the masses. In a revolving rotor, the centrifugal force remains balanced as long as the center of mass of the rotor lies along the axis of the shaft. So why balancing is necessary? The high speed of the engines and other machines is a common phenomenon nowadays. It is therefore very essential when the rotating and the reciprocating parts should be completely balanced as far as possible, otherwise vibrations will be transmitted throughout the structures and the moving parts will get loosened. So this force not only increases the loads on the bearings and stresses in various members, but also produce unpleasant and even dangerous vibrations. These are harmful to the life as well as to the phenomenon of the machine. So further we'll see what is static balancing and dynamic balancing. Static balance will be produced if the sum of the moments of the weights about the axis of rotation is zero. The dynamic balancing, we expect the sum of the centrifugal forces must be equal to zero and the sum of the couple must be equal to zero. So balancing of the rotating masses we have to be considered in different cases. Single rotating masses and single mass rotating in the same plane. Single rotating mass by two masses rotating in different plane. Balancing of different masses rotating in different plane. A different plane and same plane must be considered. So balancing of single mass by a single mass rotating in a single plane, how to do that? So we know that centrifugal force exerted by the disturbing mass m1 on the shaft, if c1 is equal to m1 into omega square into r1. The centrifugal force acts radially outwards and thus produces bending moment on the shaft. In order to counteract the effect of this force, a balancing mass m2 may be attached in the same plane of rotation as that of disturbing mass m2, such that the centrifugal force must be equal and opposite. So let m2 be the mass mass at the center, and R2 is the radius of rotation of the balancing mass. So Fc2 is equal to m2 into omega square into R2. So for equating balance, you have to consider both the equations. Fc1 is equal to Fc2. Fc1 is equal to m1 into omega square into R1. That is equal to m2 into omega square into R2. So here omega square, it is common on both sides, but it got cancelled. So m1 is equal to R1. m1 into R1, that is equal to m2 into R2, we can consider. So balancing of single rotating masses by two masses rotating in different plane. So the two conditions of equilibrium must be satisfying. So the net dynamic force on the shaft is equal to zero. Net couple net couple due to the dynamic force acting on the shaft is equal to zero. So here 1 and 2 together give dynamic balancing. So what are the two possibilities may arise while attaching the two balancing shafts? The plane of the disturbing mass may be in between the planes of two balancing masses. The plane of the disturbing masses may lie on the left or right of the two planes containing the balancing masses. So when you take two masses placed at placed at some distance, and we have to add an intermediate mass so that it has to balance both the mass. So here you can see the mass both lies are different radius but on the same side. So on the middle of both the masses, then additional mass is attached to so that it is going to have a balance. So Fc is equal to m omega square into R, Fc1 into m1 omega square into R1, Fc2 is equal to m2 into omega square into R2. So three equations are there. So sum of the centrifugal forces must be equal to 0, means Fc minus of Fc1 minus of Fc2 is equal to 0. So what is Fc must be equal to Fc1 plus Fc2. So substitute the terms m omega square is equal to m1 omega square into R1 plus of m2 omega square into R2. So that gets equated to m into R is equal to m1 into Rn plus of m2 into R2. So here substituting the given values, you'll be able to find out the unknown values. So taking the sum of the moments is equal to 0. So Fc of 1 into L minus of Fc into L2 is equal to 0. So Fc1 of L, that is equal to Fc2 into L2. So if we substitute at last, you'll be able to get M1 R1 is equal to M into R, M into R, whole thing under the root, it is considered. M1 into R1, that is equal to M into R into L into L2, it is considered. So taking two expressions, at last you'll be able to find out the required value. So the disturbing mass lies at one end of the plane of the balancing masses. So this also you can compensate by taking the necessary equations. You'll be able to equate the required balancing mass at the initial position itself. So either you can place in the middle of the plane, either you can take it in the beginning of the plane to compensate that. Both the way it is possible. So balancing of several masses rotating in the same plane, you can see here there are four different masses with four different radius. So for this, we are supposed to find out what will be the balancing condition. So to find out the balancing condition, what you are supposed to consider is take take all the given values. There will be an unknown value which has to be compensated. So you can solve this problem by two methods. One is the analytical method and another is the graphical method. So in the analytical method, what we take is some of the horizontal and vertical component must be resolved equal to 0. So here, first of all, you have to find out the centrifugal forces of the given value. Then resolve the centrifugal forces horizontally and vertical and find out the sum. So after finding out the sum, find out the magnitude of the centrifugal force. Then find out the required angle tan theta is equal to sum of the vertical forces divided by sum of the horizontal forces. So magnitude of the balancing force F is equal to m into r you can take. So, but it must be in the opposite direction. If you add that, by this you'll be able to solve the problem by untickle method.